Welcome everyone. In this talk I will summarize a case study on assessing small large language models within a retrieval augmented generation RAG workflow for academia. The breakout setting is a real administrative pain point, validating with the broad applications that arrive as bundles of annexes and supporting documents. The research question is practical if we want local deployment for privacy and cost reasons. Which small open source model gives the best trade-off between first, correctly classifying submissions as compliant or not, and second, generating useful choice-like style feedback when problems exist? In this presentation, we will review the motivation, case study designs, results, discussion, and future work related to this study. The initiative process are document-heavy and rule-bound. The case study in this paper concerns a scientific and technical mobility overall procedure at Escola Politécnica Nacional in Ecuador, where each request is submitted as a package of annexes and supporting evidence. Each annex has a strict formatting and signature requirements, and crucially, the information across the annexes must remain mutually consistent. Evaluation is performed manually. Staff review the package, identify omissions or inconsistencies, and then draft a feedback report for the applicant when issues are found. This manual upgrades long response time, and, in practice, it often misses the timeless applicants expect. The leading question is not whether large language models can write text, but whether they can act as dependable validators, classify whether a request is correct, and produce actionable checklist style feedback when it's not, because the procedure is domain-specific and highly structured. Model selection becomes non-trivial, especially when we want to run models locally at low cost. The initiative procedure under study in the mobility abroad process. It is not a single form. It is a bundle of annexes, 10 in total, plus additional supporting documentation. The challenge is combinatorial. There are 4 different application cases labeled A through D, and each case requires a different subset of annexes and evidence. Validation, therefore, has 2 layers. First, completeness. Does the case include everything that is required? Second, consistency. Do annexes agree with each other on dates, destinations, cost, and institutional approvals? The paper highlights recurring failure in mods such as missing annexes, inconsistencies across documents, and incorrect application of requirements. This kind of workflow is as good as bad for retrieval augmented generation. The LLM must reason over the submitted package while grounding its judgment in the procedural rules. The contribution of the study is a control and benchmark. 4 open source LLMs available in the LLM ecosystem are evaluated under the same retrieval augmented generation pipeline. The models are 2 Llama variants with 8 and 3 billions of parameters, and 2 DeepSeek R1 variants with 1.5 billion and 7 billion of parameters. RAG is used to run the models in the official mobility procedure documents. The study then evaluates performance on a curated dataset of 256 document package balanced across success and failure labels and across the 4 application cases. The evaluation is deliberately split in 2 tasks. Task 1 is the binary classification. Does this package comply with the procedure? And the second task is more operational. Can the model generate checklist style feedback that is accurate, complete, and actionable? That second task is especially important because in real-world or false, the value is not only in saying failure, but in explaining why and what to fix. The benchmark dataset is carefully curated to support controlled comparisons. It contains 256 document packages, each corresponding to a full application. The labels are balanced hardware success and hardware failure. The dataset is also balanced across the 4 application cases, A through D, with 32 examples per case for each label. Importantly, the entries are generated in Spanish, based on real application samples at Escola Politécnica Nacional. The labeling follows explicit criteria. A package is success only if all required attachments are present. The data across annexes is mutually consistent, information follows the specific procedural rules and formats, and the annexes contain the required signatures. This matters because it defines what the models are being asked to learn under a zero-shot prompt. Not general language understanding, but compilance checking against a structured rule set. The benchmark starts with 4 models, all run locally for one llama. Two are llama family models from Meta and llama 3.1 at 8 billion parameters and llama 3.2 at 3 billion parameters. Both are standard dense color-only transformed and use a grouped query attention, which is designed to reduce inference costs. Also, both have a multilingual native support. The DeepSeeker 1 family represents a different design point, emphasizing reasoning and using a mixture of experts architecture. The study includes a 1/2 billion and 7 billion DeepSeeker 1 variant. An important empirical finding appears immediately. DeepSeeker 1 at 1/2 billion parameters produce outputs that are often empty or highly repetitive under the fixed workflow. From an operational perspective, this is a key reminder. A model can be small and open source, but still failing reliability. The experimental setup uses retrieval augmented generation to run the LLMs in the official mobility procedure documents. Conceptually, this is crucial. The model should not embed rules. It should retrieve the relevant procedural text and then apply to the applicant package. The retriever is built in 3 steps. First, the corpus is chunked using a simple character-based sliding window, chunks of 500 characters with an overlap of 100 characters. Second, each chunk is embedded using the sentence transformer model. And third, embeddings are stored locally in a MPC file along with JSON metadata. At different times, the same embedding model encodes the input codes and similarly retrieves to the top 5 most relevant chunks. Finally, the system builds a composite prompt by combining the applicant's document with the retrieval procedural context. The LLM then produces the classification decision and the feedback checklist. The evaluation is structured to reflect the operational needs. For the classification task, the output is simple, success or failure, and performance is assessed using the standard confusion matrix metrics, precision, recall, and F1 score. The support is the full dataset of 256 cases. For feedback generation, the paper introduced a 100-point rubric with 5 equally weighted dimensions. This captures whether the model detects the presence of inconsistencies, how fully it covers true errors, whether its diagnostics are correct and grounded, whether its advice is actionable and clear, and whether latency is acceptable. Crucially, feedback is evaluated using a mixed protocol. Automatic evaluation applies an LLM as a judge approach to 100% of generated outputs. Manual evaluation applies the same rubric to a 55% random sample using fixed or random seed. This design acknowledges that automatic graders are convenient but may not align with human judgment in administrative context. In this section, we'll review the results of both task classification task and feedback generation. Let's start with the classification task. Here, the goal is to identify whether the submitted package is correct and the paper report's precision recall an F1 score. The useful way to read these metrics is to think of failure detection as the positive class. High recall means we catch most problematic requests. High precision means we avoid falsely rejecting correct requests. Three models remain after excluding DeepSeeker 1.5 billions. Llama 3.2 at 3 billion parameters achieves the highest precision of 0.96 and the best F1 scored at 0.7. In other words, when it flags a package as incorrect, it is usually right, but it misses a non-trivial fraction of failures, reflected in its recall of 0.56. By contrast, Llama 3.1 at 8 billion parameters achieved the highest recall at 0.84, meaning it defines most incorrect procedures, but at the cost of lower precision at 0.55. More false positive. DeepSeeker 1 with 7 billion of parameters sits between them with a more balanced precision and recall around 0.66. Now we turn to feedback generation, and first we look at the manual evaluation results. Here ITMA evaluators scores the checklist style outputs using the 100-point rubric on a random 25% sample of the dataset. Here we can see that Llama 3.1, 8 billion of parameters, performs the best, with an average score of 62.45 out of 100. DeepSeek R1 with 7 billion parameters follows as 53.21, and Llama 3.2 with 3 billion parameters scores 50.16. The paper interprets this as a meaningful separation. Llama 3.1 is preferred from the user's perspective, presumably because its feedback is clearer, more grounded, or more actionable. Latency is also reported. Llama 3.2 with 3 billions is the fastest, about 1.12 seconds. And the DeepSeek R1 with 7 billion parameters is notably slower, about 5 seconds. Operationally, this slide already suggests the curve rate of speed versus perceived feedback quality. When the rubric applied automatically across all 256 outputs, the picture changed. Scores cluster fairly. DeepSeeker 1 with 7 billion is slightly highest at 74.48, while Llama 3.1 with 3 billions and Llama 3.1 with 8 billions are very close at 72 and 72.59, respectively. The paper notes that the differences here are small, on the order of a couple of points, suggesting that the automatic judge views these models as roughly comparable on this task. However, the key insight is the discrepancy between automatic and manual scoring. When we compute automatic minus manual, the gaps are large, plus 10 points for Llama 3.1 and plus 22 points for Llama 3.2 and plus 21 points for DeepSeek 1 with 7 billions. The mean absolute error between the two evaluation models is about 18 points. This is a strong empirical warning about relying solely on LLM as a judge for bureaucratic feedback quality. Automatic evaluation is scalable, but it may not track human preferences for clarity, usefulness, or the avoidance of superior findings. Bringing the results together, model choice depends on what the institutional values most. If the primary goal is to minimize false alarm rejecting corrupt application, then Llama 3.2 with 3 billion parameters is attractive because its precision is strongly high. But the cost is recall. It misses many failures, which is risk in compliance workflows. If the primary goal is to catch problematic requests and provide feedback that human reviewers find useful, Llama 3.1 at 8 billion parameters is the strongest candidate. It has the highest recall on classification and the best manual feedback score while keeping latency around 2 seconds on average. DeepSeek 1 with 7 billion parameters is a plausible middle ground on classification and it has the highest automatic feedback score, but it is slower and its manual feedback score is currently below Llama 3.1, which may matter more for adoption. Therefore, consistent with the author's conclusion, the recommended model for reliable validator and reporter agent under this fixed RAG pipeline is Llama 3.1 with 8 billion parameters. For the future works, first, although the dataset is grounded in real institutional example, the entries are manually generated. A key next step is to well anonymize dataset from real submissions to ensure ecological validity. Second, the experiment use a single prompt in a zero-shot setting. A natural station is to compare zero-shot and few-shot prompting under the same workflow to test whether small models can be stabilized with minimal demonstration. Third, because the RAG is an architectural choice, we should quantify its contribution directly via an evaluation study. Evaluating the same task with and without retrieval augmented generation. Finally, the model evaluation will be benefit from multiple independent evaluators, enable inter-rater reliability estimates, and more robust conclusions about feedback quality. Overall, the work shows that small local models can provide meaningful automation for administrative validation, provided we benchmark carefully and select models based on the right operational criteria. Thank you for your attention.